Imagine an icy snowball hurtling through space from another star. In July 2025, astronomers spotted just such an interstellar stranger, Comet 3I Atlas, blazing into our solar system on a fast hyperbolic track. This visitor is extraordinary. It's only the third interstellar object ever detected. After ʻOumuamua in 2017 and Borisov in 2019, already a hazy glow surrounds it. A fuzzy coma and sweeping tail of gas and dust that mark a classic comet. But 3I Atlas is no ordinary comet. It speeds along at over 130,000 miles per hour, and its orbit is so steep it will never return. Even before it neared the Sun, this alien wanderer was wowing scientists with its sheer scale. Hubble data hint its nucleus could be miles across, making it possibly the largest interstellar comet yet seen. Far from the Sun, at distances where most comets remain frozen solid, 3I Atlas has been gushing water and carbon dioxide ice into space. Space telescopes detected hydroxyl, a breakdown product of water, streaming off the nucleus almost 3 times farther from the Sun than Earth, and JWST measurements show an unusually high carbon dioxide to water ratio in its makeup. In plain terms, it's spraying water like a fire hose in deep space, an eruption of volatiles at 2 to 3 astronomical units that no ordinary comet would manage. This intense activity is already feeding its bright tail, confirming 3I Atlas as a genuine active comet rather than a bare rock. Yet puzzles abound. 3I Atlas may be ancient, possibly 7 to 8 billion years old, even older than our entire solar system. Why would such an old ice ball suddenly ignite so far from the Sun? And what can its bizarre behavior tell us about other star systems? Each interstellar visitor has rewritten our textbooks. One was bone dry, another rich in unexpected gases, and now Atlas is bursting forth in ways no one predicted. What stories does this cosmic messenger carry from beyond our Sun? To answer that, we must go back to where it all began, the discovery of 3I Atlas, which we'll explore next. In early July 2025, the NASA-funded Atlas Sky Survey in Chile detected a moving point of light that captured astronomers' attention. The object, later named 3I Atlas, appeared as a faint speck, about 18th magnitude, roughly 4.5 astronomical units from the Sun and 3.5 AU from Earth. Its motion was unusual. It was traversing space at roughly 61 kilometers per second, 140,000 miles per hour, relative to the Sun. Early orbit fits hinted at a very eccentric trajectory. For a brief moment, models suggested the path might even brush near Earth's orbit. The MPC noted the object on its Near-Earth Object Confirmation page as astronomers scrambled for more data. But further observations quickly changed the story. Within days, telescopes around the world, both professional and amateur, gathered more astrometry. Archival images were re-examined, and pre-discovery detections from Atlas and the Zwicky Transient Facility in late June were identified. These additional data showed the orbit was not headed toward Earth at all. Instead, the calculations revealed a highly hyperbolic, unbound orbit. Calculations confirmed what the speed suggested. This visitor had come from afar. The orbital eccentricity was far above 1, and its excess velocity, about 58 kilometers per second, meant it could not be gravitationally captured by the Sun. In other words, 3I Atlas was on a one-way trajectory through the solar system, never to return. The MPC officially classified it as an interstellar comet, 3I Atlas, on July 2nd. Its speed and hyperbolic path made clear it was not native to our solar system. In that instant, astronomers realized they had found only the third known object of interstellar origin, after ʻOumuamua and 2I Borisov. The discovery ignited excitement in the community. NASA and other agencies swiftly pointed powerful telescopes at the comet, including the Hubble and James Webb Space Telescopes. ESA astronomers noted that ground-based observatories in Hawaii, Chile, and Australia were quickly mobilized to keep track of 3I Atlas. News outlets reported on the third interstellar visitor to our solar system. Early analysis, for example by a team at Oxford University, even speculated that this might be the oldest comet ever seen, perhaps over 7 billion years old. At the same time, scientists emphasized that 3I Atlas poses no threat to Earth. Its trajectory keeps it well beyond 1.8 astronomical units from our planet, and they framed the finding as a thrilling scientific opportunity rather than a danger. As teams raced to characterize this rare find, the next question was, what exactly is 3I Atlas itself? In the following days and weeks, telescopic imaging and spectroscopy targeted the object's coma and tail. Hubble observations, for example, constrained the nucleus size to just a few kilometers across. Astronomers measured its record high velocity and began analyzing the composition of its outgassing. In the next section, we'll take a closer look at the visitor's physical nature, its dimensions, its blistering speed, and the icy structure that gave 3I Atlas its comet-like appearance. Astronomers estimate that 3I Atlas's solid nucleus is only a few kilometers across. Hubble's sharp image puts an upper limit on the nucleus diameter at about 3.5 miles, 5.6 kilometers, though it could be much smaller if the surface is very dark. In visible light, the icy core is hidden in a glowing cloud, so its exact shape isn't directly seen. We infer it is probably nearly round, but shrouded by dust. Typical comet nuclei reflect only a few % of sunlight. So if 3I Atlas is similarly dark, that is why a nucleus only kilometers wide can appear as bright as it does. In Hubble's July 2025 image, the nucleus lies at the tip of a bluish teardrop-shaped cocoon of dust. This teardrop form traces the heavy bombardment of sunlight on the warm side of the comet, blasting off curtains of fine particles that envelop the solid core. Even far from the Sun, 3I Atlas already carried a thick coma of gas and dust. Hubble saw a bright plume streaming from the sun-facing side of the nucleus. By late August, ground-based telescopes like Gemini South captured a clear growing tail. Solar heating of the comet's surface, or of icy grains around it, causes jets of vapor to launch dust into space. The result is a shimmering, fuzzy atmosphere and tail. Sunlight pressure and the solar wind then sweep that dust and gas back into a classic cometary tail. Viewed through powerful telescopes, 3I Atlas appears as a glowing greenish-white ball with a faint trail behind it. Hubble's picture shows background stars streaked by the comet's motion, while the comet itself shines as a compact bright blue cloud. Amateur images have even hinted at a subtle green hue around the comet, a common cometary glow caused by carbon-bearing molecules fluorescing under sunlight. JWST's infrared snapshots confirm the presence of specific ices. Spectral line data clearly pick out water vapor and a carbon dioxide-rich coma, often described as a CO2 fog. In summary, through Hubble and JWST, we see an active ice-rich comet hurling through space, its nucleus enveloped by a thick, dust-laden coma and a developing tail. The comet's speed and trajectory are unprecedented. Even when first discovered, 3I Atlas was moving at roughly 210,000 kilometers per hour, about 58 kilometers per second relative to the Sun. As it falls toward the Sun, gravity will boost its speed still higher. Near perihelion, closest approach on October 29, it will be streaking around 68 kilometers per second, about 245,000 kilometers per hour. That is far faster than any other comet we've seen. Its path is extremely hyperbolic, eccentricity approximately 6.1, a one-way trajectory that cuts through the solar system without looping back. In other words, this visitor is tearing through on a steep, straight course, unlike normal long-period comets that return again. What makes 3I Atlas so visibly active is its rich supply of ices. NASA's Swift satellite detected it spewing water and hydroxyl even when the comet was about 2.9 astronomical units from the Sun, nearly 3 times Earth's distance. At that distance, water ice should normally be frozen solid. Yet 3I Atlas was shedding water at roughly 40 kilograms every second, literally like a fire hose of vapor. This implies a very large active area, roughly 8% of the comet's surface, far higher than the 3 to 5% typical for ordinary comets. Observations by NASA's SphereX mission further show a vast cloud of carbon dioxide gas enveloping 3I Atlas. In fact, 3I Atlas's coma is unusually dominated by CO2 and water. Spectral data and infrared imaging reveal significant CO2 emission alongside the water vapor. The picture emerging is that icy grains and chunks surround the nucleus and, warmed by the sun, release gas like miniature steam jets. Altogether, 3I Atlas is far more vigorously outgassing than typical solar system comets. a result of its volatile, rich makeup, and presumably many billions of years of cosmic baking. This remarkable activity and speed raise a tantalizing question. Where did this interstellar visitor come from? In the next section, we turn to 3I Atlas's possible birthplace among the stars and the long galactic voyage that delivered it to our solar system. Astronomers believe 3I Atlas did not form around our Sun at all, but in a distant, ancient part of the Milky Way. Its trajectory and speed suggest it hails from the galaxy's thick disk, a stellar population of very old, metal-poor stars. Models show that if 3I Atlas came from the thick disk, it could be on the order of 7 to 11 billion years old, meaning it may have formed long before our 4.6 billion-year-old Sun. In fact, some studies estimate its age at up to 14 billion years. In other words, by the time Earth and its planets were born, this icy comet was already an ancient interstellar wanderer. Once it grew large enough to stop growing, gravity would have begun to throw 3I Atlas out of its birth environment. Its home system's giant planets likely migrated inward in the early days, scattering smaller bodies outward. Such close encounters can accelerate comets to escape velocity. In other words, a giant planet, or even a passing star, could have acted as a cosmic slingshot, hurling 3I Atlas into the void. One simulation from Planetary Science shows that early migrating gas giants routinely eject icy objects into interstellar space. After this dramatic ejection event, or perhaps several such events, the comet was stripped from its system and set on an independent orbit through the galaxy. After that, 3I Atlas began its long voyage through the galaxy. For eons, it wandered the dark spaces between stars. In fact, based on its velocity, scientists calculate that 3I Atlas may have been drifting for billions of years. Over that time, it would have crossed the galactic plane, dipped in and out of spiral arms, and even skimmed past other stars. One recent study found it likely passed within a few light years of at least 25 known stars over the last 10 million years. NASA summarizes this long journey. 3I Atlas formed in another star system and was somehow ejected into interstellar space. For millions or even billions of years, it has drifted until it recently arrived at our solar system. The comet finally approached from the direction of Sagittarius toward the galactic center, carrying with it the history of countless encounters in the Milky Way. Captured by Hubble, 3I Atlas appears as a tiny blue-white fuzzball surrounded by wisps of gas and dust. Even after its aeons in the cold, its image reveals a diffuse coma, evidence that sunlight finally began sublimating its ices as it neared our Sun. Above, the Hubble Space Telescope image of 3I Atlas on July 21, 2025, shows the faint cocoon of material around the nucleus. But by then, the comet's surface had been weathered by space. Drifting for billions of years under constant cosmic ray bombardment, 3I Atlas developed a hard, processed crust. Observers note that this prolonged exposure stripped the comet of surface hydrogen, leaving a drier, less volatile shell. In effect, the comet's volatile ices have been slowly baked and eroded, ice molecules broken apart and dark organic compounds enriched by high-energy radiation. JWST and other telescopes even infer a cooked surface layer, where carbon dioxide ice has reformed after cosmic rays broke apart other ices. Thus, 3I Atlas has spent most of its life as an ultra-cold, travel-worn relic of its ancient birthplace, preserving the imprint of galactic history on its tiny frame. At last, after its epic galactic odyssey, 3I Atlas swept into the inner solar system and into our view. Ground-based telescopes swung into action, and on July 1st, 2025, the Atlas Survey Telescope in Chile detected a faint, moving object in Sagittarius. This report, Comet 3I Atlas, was soon confirmed as an interstellar wanderer. In that moment, humanity's instruments had caught sight of a visitor that had traveled for millennia. Next, we turn to how astronomers observed and tracked 3I Atlas from Earth. Observatories around the globe raced to track 3I Atlas as soon as it was announced on July 1st, 2025. Within days, networks of telescopes from Hawaii to Chile and Australia pulled archival images and pointed their instruments at this interstellar visitor. ESA and NASA quickly mobilized flagship observatories. Hubble and James Webb both locked onto Atlas, as did a fleet of space-based telescopes including SWIFT, SPHEREX, and even TESS. Each brought different strengths. In late July, Hubble imaged the comet's nucleus at 277 million miles out, revealing a teardrop-shaped cocoon of dust around the icy core. By August 6th, JWST trained its infrared near-spec spectrograph on Atlas, identifying its chemical makeup. At the same time, SWIFT's UV camera hunted for the signature of water by catching OH radicals from sublimating H2O. Even Mars orbiters and other deep space missions were ready to snap pictures of Atlas as it zoomed past. Every observation, the digital images and spectra, was used to measure dust and gas production rates. Indeed, SWIFT's detection of OH light implied a water production rate on the order of tens of kilograms per second. In short, astronomers collected a rich suite of data: broadband and narrowband images of the coma and tail, high-resolution spectra revealing the chemicals present, precise position fixes for orbital tracking, and measurements of the comet's gas outflow and dust ejection rates. All this had to happen fast. 3I Atlas is on a hyperbolic escape trajectory, eccentricity approximately 6, racing through the inner solar system. It will reach closest approach to the Sun, approximately 1.4 astronomical units on October 30, 2025, then rapidly fade. In fact, models showed Atlas would remain readily visible to telescopes only through September 2025, before it passed too near the Sun to observe. By early December, it re-emerges on the far side of the Sun, but only as a faint smudge. In other words, astronomers had only a narrow window of weeks to gather high-quality data. This sense of urgency explains the coordinated rush. Archival images from Atlas's Discovery survey and Pan-STARRS were scoured for earlier sightings, and every available telescope was booked solid. For instance, as soon as its interstellar nature was confirmed, teams retroactively found pre-discovery Atlas images dating back to June 14, 2025. Thanks to this global campaign, streaming images and spectra from space and ground-based observatories, astronomers now have an unprecedented dataset on 3I Atlas. With these observations in hand, the next question is obvious. How does Atlas compare to the two interstellar objects seen before? 3I Atlas is the third known interstellar object, joining 1I ʻOumuamua, 2017, and 2I Borisov, 2019. Each visitor has surprised us in different ways. ʻOumuamua was like nothing seen before, a dry, rocky intruder, whereas Borisov was clearly a comet, albeit an extraordinarily icy one. Now Atlas appears as a comet too, but with yet another chemical twist. To put these differences into context, let's recall the key features of each. 1I ʻOumuamua, October 2017, blazed through the solar system as a rocky, cigar-shaped object. It spun roughly every 7.3 hours and varied hugely in brightness, by a factor of approximately 10, implying an extreme length-to-width ratio unmatched by any known asteroid. Despite zipping past the Sun, ʻOumuamua showed no visible coma or tail. Its surface had no detectable water or ice. In other words, it behaved more like a bare asteroid than an active comet. Its reddish color, from cosmic ray weathering, and its rapid motion, nearly 26 kilometers per second, left astronomers puzzled as to its true nature. In short, ʻOumuamua was a dry, elongated loner with barely a hint of volatiles. By contrast, 2I Borisov, late 2019, behaved like a garden-variety comet at first glance. It developed a greenish coma and long tail as sunlight heated its ices, but its chemistry turned out to be exceptional. Observations with Hubble and the ALMA radio array showed that Borisov's gas was overwhelmingly rich in carbon monoxide. In fact, its CO abundance was approximately 9 to 26 times higher than water, a ratio far above that of any solar system comet observed within 2 astronomical units. This suggested Borisov formed in an extremely cold region, perhaps around a red dwarf star, where CO ice was abundant. Its nucleus was only about 0.6 kilometers across, roughly 9 football fields long, but it otherwise behaved like a typical icy body, jets of gas and dust, a classic tail, etc. The key surprise was its CO-rich composition, which hinted at a comet from a very different kind of stellar nursery. 3I Atlas now adds a third flavor. It too shows an active coma and tail. Images from Gemini and Hubble clearly reveal its dust cloud, but its outgassing signature is yet another twist. In fact, Atlas appears to have one of the highest CO2 to water ratios ever seen in a comet. Early swift UV measurements, via OH emission, confirm that Atlas is blasting water off its surface even far from the Sun. In terms of ice content, Atlas is therefore water and CO2 rich. In short, ʻOumuamua was dry and asteroid-like, Borisov was a hyper-icy CO-rich comet, and Atlas is a vigorously outgassing comet with abundant water and CO2. Each new interstellar interloper has upended our expectations. ʻOumuamua taught us that some extrasolar objects can arrive as bare, elongated rocks. Borisov showed that others carry ultra-rich ices. And Atlas reveals yet a third possibility with familiar volatiles gushing off it. As one scientist put it, detecting water in Atlas is like reading a note from another planetary system, proof that the ingredients for life's chemistry are not unique to our Sun's neighborhood. Together, these three wild wanderers challenge our assumptions about planet formation across the galaxy. Each tells a part of the story. Rocky fragments, CO2 ice worlds, and water-bearing comets all exist around other stars. Next, we'll ask what Atlas's unique mix of ices and dust implies for the origins of planets and solar systems beyond our own. One leading idea is that 3I Atlas formed in extreme cold, beyond the CO2 snowline of its birth system. In a distant protoplanetary disk region, temperatures would have been low enough to freeze carbon dioxide ice directly. Observers note that 3I Atlas's chemistry suggests that it may have originated possibly near a CO2 ice line or in an unusual radiation-rich environment. NASA astrochemist Stephanie Millam points out the object may have formed where the carbon dioxide ice line is, so pretty far out in that disk. In such a frigid outer disk, solid carbon dioxide would dominate its ices, giving the comet a built-in excess of CO2. Intense ultraviolet light or a low water abundance in its natal system could accentuate this effect, skewing its composition towards CO2. In short, 3I Atlas likely began life as a CO2-rich planetesimal in the cold outskirts of another solar system. Cosmic weathering may have added to the effect. Models suggest 3I Atlas has been roaming the galaxy for billions of years, exposing it to continual cosmic ray bombardment. Over time, this radiation can cook a comet's surface, breaking up complex ices and leaving a carbon-rich crust. Millam notes that such exposure could create a cooked shell on 3I Atlas, where CO2 ice becomes concentrated. In this picture, energetic particles gradually disintegrate its surface H2O, turning it into escaping H2, while leaving behind CO2 and carbon residues. The result is a deep, insulating crust of dark refractory material. That crust would keep the interior water ice frozen until the comet gets much closer to the Sun, while any CO2 closer to the surface or created by radiation can sublimate at the lower temperatures encountered in the outer solar system. In other words, surface processing by cosmic rays could deplete near-surface water and make the comet vent CO2 preferentially. The comet's internal structure may also play a role. Observations found no prominent dust tail at first. Instead, the coma shape and polarization imply unusually large dust grains. This hints that 3I Atlas's nucleus could be very porous or loosely bound. One hypothesis, supported by Swift and Gemini images, is that chunks of icy debris break off the surface and then rapidly sublimate, feeding the distant coma. Wired magazine describes this as small fragments of ice detaching from the nucleus and vaporizing in sunlight. In effect, sunlight penetrating into pores or cracks can heat subsurface pockets of volatile-rich ice, causing them to vent even when the ambient temperature is extremely low. Such miniature cryovolcanic or pressure-driven jets have been proposed. Some researchers suggest that 3I Atlas's near absolute zero activity might be explained by localized cryovolcanism or pressure-driven release of trapped volatiles. If pockets of gas, like CO or N2, were trapped under an insulating layer, they could erupt suddenly as the outer crust fractures, mimicking cryovolcanic eruptions on icy moons. Thermal layering is another factor. If 3I Atlas has a thick dust or carbon layer, solar heat takes longer to reach interior ices. Carbon dioxide has a lower sublimation temperature than water, so any solar energy that does penetrate will drive CO2 off first. As Universe Today explains, if the nucleus is difficult to heat, CO2, which has a lower melting point than water, would be sublimated first, accounting for the lopsided ratio, despite having plenty of water stored in the nucleus waiting to be released. In practice, this means 3I Atlas can outgas strongly at large distances through CO2, yet remain water poor until it gets much closer. Once nearer the Sun, we do expect water activity to rise. Indeed, 3I Atlas is already showing some rising OH signals, but its early volatility appears dominated by these exotic conditions. Each of these ideas, cold formation, radiation processing, porous structure, trapped gases or cryovolcanic vents, could contribute. No single explanation is proven yet, and scientists are eagerly debating which are most important. As one researcher puts it, every interstellar comet so far is a surprise. 3I Atlas's bizarre chemistry and activity is rewriting what we thought we knew about how planets and comets form around stars. In the next section, we'll explore what these clues mean for planetary science, how this strange visitor informs our understanding of planetary systems, protoplanetary disks, and the universal processes of planet formation. Infrared surveys of 3I Atlas reveal a reddish, organic-rich surface reminiscent of D-type asteroids and primitive carbonaceous bodies. In fact, astronomers find its spectral reflectance can be modeled by a mix of Tagish Lake meteorite material, a dark, carbon-rich chondrite, and water ice. This implies 3I Atlas is laden with complex organics and silicate dust, with carbonate minerals also present. Essentially, a dirty snowball of rock and ice akin to the most primitive asteroids and comets in our own solar system. Detailed spectroscopy by NASA's SphereX and JWST missions highlights an unusual volatile inventory. Both find an abundance of carbon dioxide, CO2, in Atlas's coma, far higher than any comet seen before. By contrast, carbon monoxide, CO, appears only in trace amounts. The coma is CO2 rich, but CO poor. One interpretation is that Atlas formed in a relatively warm part of its parent disk, near the CO2 ice line, or spent a long time warmed by its star, so that its original CO ice boiled off long ago. In other words, the comet looks more like a thermally processed Jupiter family comet from the inner system than a pristine, icy body from the far outer reaches. Scientists also suspect 3I Atlas has a layered interior. The lack of abundant water vapor and the necessity of an insulating layer, hinted at by the low sublimation of water ice, suggest a thick crust of refractory dust covering an ice-rich core. In this picture, a dark mantle of organic dust keeps heat from penetrating deeply. Below that crust lies relatively pure water ice. Such stratification could explain why CO2, with a higher vaporization temperature, is readily escaping, while much of the water ice remains locked below. Evidence of tiny icy grains being shed into space supports this model. Observations show micrometer-sized water ice particles in the coma, likely lofted off by more volatile CO2 and CO jets, and then sublimating far from the nucleus. Ultraviolet measurements even detected H2O and OH radicals at tens of thousands of kilometers out, indicating icy grains were releasing water well beyond the solid nucleus. In effect, 3I Atlas is spewing off fine ice dust through its coma, much as distant comets do when sunlight heats exposed pockets of ice beneath a dusty crust. All told, 3I Atlas is thought to be a low-density rubble pile, a loosely bound dirty snowball with many pores and voids. Its nucleus appears only a few hundred meters across, at most a few kilometers, and is encrusted in dark dust. It's not a solid rock, but an aggregate of ices and dust, with overall density well under that of water ice. Such a structure is typical of comets, which are often compared to loose chunks of compacted snow and organics. This rich compositional portrait of 3I Atlas, organics, ices, and CO2-rich gases, feeds directly into the next chapter of our story. In the next section, we turn from chemistry to motion, the orbital data and hyperbolic trajectory that first revealed Atlas's truly interstellar origin. In orbital mechanics, an interstellar object follows a hyperbolic trajectory. Its orbital eccentricity exceeds 1, and its speed outpaces the Sun's escape velocity. In other words, it has a positive hyperbolic excess speed at infinity. 3I Atlas meets this definition. Its orbit has been computed with eccentricity on the order of 6, far above the parabolic cutoff of 1. Such an extreme orbit means it never made a closed loop around the Sun. Observatories confirm that 3I Atlas's incoming speed relative to the Sun is enormous. Its hyperbolic excess is approximately 57 kilometers per second, far above the approximately 42 kilometers per second escape speed at 1 astronomical unit. This is much faster than any comet or asteroid bound to our system, and even exceeds the approximately 26 kilometers per second and approximately 32 kilometers per second speeds of the previous interstellar visitors, 1I ʻOumuamua and 2I Borisov. In fact, as NASA notes, measurements show 3I Atlas is moving too fast to be bound by the Sun's gravity. It is on a hyperbolic trajectory and will simply continue out into interstellar space. The path and orbit of 3I Atlas have been mapped by a worldwide campaign of observations. After its discovery by the Atlas Survey Telescope on July 1, 2025, astronomers scoured archival images for earlier sightings. NASA reports that pre-discovery data from multiple Atlas stations and the Zwicky Transient Facility extend observations back to mid-June 2025. Space observatories also contributed. For example, NASA's TESS satellite fortuitously captured the object in images from early May through June 2025. Each new astrometric measurement from ground-based telescopes, Hubble, JWST, and others, was added to orbital models. In fact, the JWST team notes that the telescope tracked 3I Atlas using an ephemeris built from astrometry supplied by a large number of optical observers. All this data was fed into NASA's JPL Horizon system to solve the orbit. As a result, the trajectory of 3I Atlas is now very well determined. The computed orbit of 3I Atlas leaves no doubt it is unbound. Latest fits give an eccentricity approximately 6.1, with very small uncertainty. At discovery, about 4.5 astronomical units from the Sun, 3I Atlas was already traveling approximately 61 kilometers per second relative to the Sun, a speed that only increases as it falls toward perihelion. By contrast, even the first interstellar object, ʻOumuamua, had eccentricity approximately 1.20 and Borisov approximately 3.36. The hyperbolic excess velocity of 3I Atlas, approximately 57 kilometers per second, is far higher than those of ʻOumuamua, approximately 26 kilometers per second, or Borisov, approximately 32 kilometers per second. In practical terms, this means 3I Atlas is moving too fast to have been captured by the Sun. Continued observations have steadily refined the orbit. As more imaging data poured in, including TESS pre-covery and ongoing astrometry, orbital solutions converged. By mid-2025, the uncertainty in eccentricity was already tiny. These precise trajectories show that 3I Atlas's path missed the planets by a safe margin. For example, it never came closer to Earth than approximately 1.8 astronomical units, and only a few million kilometers to Mars. No close planetary flyby occurred that could have slingshotted it to such a speed. In short, nothing in the solar system can impart such a trajectory. The only consistent explanation is that 3I Atlas arrived from beyond our system, an interstellar visitor on a high-speed one-way flyby. Throughout, astronomers emphasize that 3I Atlas's orbital data are fully compatible with a natural origin. Its hyperbolic excess motion and eccentricity greater than 1 are calculated from solid observations. Combined with comparisons to ʻOumuamua and Borisov, this confirms that no gravitational boost within the solar system could have produced its speed and path. In other words, 3I Atlas could not have been flung out from our system. It must have come in from another star's neighborhood. Astronomers can read Atlas's story in its motion and makeup. Its blazing speed and path show it hails from outside the Sun's domain, likely from the Milky Way's old thick disk. That disk is home to ancient stars, so Atlas itself must be truly ancient, on the order of 7 to 10 billion years old, far older than our 4.6 billion-year-old Sun. In other words, 3I Atlas is a frozen time capsule from another star system's youth. It carries pristine material and chemistry from the era when its parent star and planets formed. The comet's chemical fingerprint is telling. Spectra from JWST and other telescopes show Atlas's coma is dominated by carbon dioxide, with only trace water and modest carbon monoxide. In fact, its CO2 to H2O ratio is the highest ever measured in a comet. Observers also find organic gases like carbonyl sulfide, and even metals such as nickel in the coma. This unusual mix of ices and dust points to a very cold, volatile-rich birth environment. For example, a CO2-rich nucleus suggests Atlas may have formed near the CO2 snow line of its original protoplanetary disk, the region where temperatures were low enough for carbon dioxide to freeze out. In that frigid inner disk, it would accumulate carbon dioxide, ice, and organics not seen in ordinary comets of our system. Other clues hint that Atlas was thermally processed before being flung out into space. The comet's surface is extremely dark and red and seems to have a cooked crust. Much of the easy-to-evaporate CO ice appears to be gone. It's as if Atlas spent time closer to its parent star, heating up and driving off those volatiles. Indeed, detection of nickel tied up in volatile compounds like nickel carbonyl indicates past warmth. In short, the evidence suggests Atlas formed in a distant, cold part of its solar nebula, rich in CO2 and water ice, then drifted inward enough that its outer layers lost CO and other ices before being ejected into interstellar space. These findings show that Atlas is not just another Oort cloud comet from our own sun. It's a new species of comet from a different system. Its chemistry is unlike any solar system comets. For example, it's strongly depleted in diatomic carbon relative to cyanide, a trait set at its formation billions of years ago. This exotic signature implies it formed in a different part of its home system's disk than most comets. In broader terms, Atlas's unique makeup underlines the diversity of planetary systems. Not every system creates comets like ours. Studying Atlas expands our view of what kinds of icy bodies other stars can throw out into the galaxy. Ultimately, 3I Atlas is indeed an interstellar time capsule, a preserved record of planet formation around an alien star. Being potentially billions of years old, it carries clues about the conditions in its parent protoplanetary disk long before the Earth existed. By analyzing its ices and dust, astronomers hope to reconstruct that ancient environment and compare it to our own solar system's history. As Atlas zooms back into space, leaving fewer secrets behind, it already has captured imaginations on Earth. As 3I Atlas swings through its closest approach, it will soon begin its outbound flight. NASA models show 3I Atlas reached perihelion, its closest point to the Sun, around October 30, 2025, at about 1.4 astronomical units, just inside Mars' orbit. After that, it will speed past the inner planets, brushing Mars in early October, then swinging by Venus and Earth, and finally pass about 0.36 astronomical units from Jupiter in March 2026. From there, it will be on its way out of the solar system. In other words, 3I Atlas follows a hyperbolic path and will escape the Sun's grasp, never to return. Its brightness, however, will not last. NASA notes that 3I Atlas is visible to telescopes now, but will soon fade into the Sun's glare. Observers expect it to remain in view only through early fall 2025. By late October, it will pass behind the Sun and become unobservable, only to reappear faintly in our pre-dawn sky by early December. In fact, recent reports already note the comet has now faded from view in October, though it will re-emerge after mid-November. Once past perihelion, 3I Atlas will recede into the outer solar system, and the sunlight driving its activity will weaken. Its icy coma and tail will steadily diminish, and within a few months, the object will become too dim, even for large telescopes. In short, the window to see 3I Atlas is closing fast. Before it disappears completely, astronomers must capitalize on every observation. One wildcard is outburst or fragmentation. In 2020, for example, interstellar comet 2I Borisov unexpectedly brightened twice as it neared the Sun, a clear sign its nucleus was breaking up. 3I Atlas could similarly erupt or shed pieces as solar heating intensifies. Scientists are therefore watching closely for any sudden jets, flares, or breakup events, because such behavior would teach us about its internal structure. Teams around the world are lining up every available telescope while the comet is still active. Space observatories like the Hubble Space Telescope and the James Webb Space Telescope have already been trained on Atlas, and more are planned. For example, Hubble will run ultraviolet spectroscopy on the comet in November 2025 to probe its gas composition, and JWST is set to point its infrared instruments at the comet again in December 2025. NASA also lists assets like the Swift UV telescope, TESS, and even the Keck Observatory on Hawaii as part of the campaign. On the ground, major telescopes continue imaging the fading coma and tail. All told, these observatories will measure 3I Atlas's volatile chemicals, dust production, and nucleus size before the comet dims. Looking further ahead, astronomers are preparing for the next interstellar visitor, since we won't catch Atlas with a spacecraft. For instance, ESA's Jupiter Icy Moons Explorer will be in position to observe 3I Atlas just after perihelion in November 2025, using cameras and spectrometers. Its data are expected by early 2026. The European Space Agency is also building Comet Interceptor, launch approximately 2029, a spacecraft park, and waiting for a future long-period or interstellar comet. And powerful surveys like the upcoming Vera Rubin Observatory will quickly find many more such wanderers. Astronomers expect even a 4I interstellar object within a few years. In the end, the race is on to squeeze out every bit of science from 3I Atlas before it slips into the depths. Scientists hope to lock down its volatile inventory, dust properties, and any unusual behavior in these last observations. Each measurement refines our picture of how an interstellar comet behaves under solar heating and what materials it carries. As 3I Atlas fades, its legacy will guide us in spotting and studying the next visitor from beyond, setting the stage for future interstellar discoveries. In Hubble's July 2025 view of 3I Atlas, the comet's nucleus is seen enveloped in a bright, teardrop-shaped dust coma, a vivid contrast to 1I ʻOumuamua, which showed no detectable coma at all, and even to 2I Borisov's relatively normal cometary tail. And 3I Atlas is moving far faster than its predecessors, roughly 61 kilometers per second, around 137,000 miles per hour, when discovered, compared to approximately 26 kilometers per second for ʻOumuamua and approximately 32 kilometers per second for Borisov. In other words, Atlas arrived on a very different speed and with a very different look. ʻOumuamua appeared asteroidal and dry. Borisov behaved like a run-of-the-mill solar system comet, but Atlas shows unexpected activity and composition. Early observations of Atlas revealed behavior that puzzled scientists. Even when it was approximately 3 to 4 astronomical units from the Sun, 3I Atlas was already spewing water vapor and gas at enormous rates. Unusually, Atlas's coma was dominated by carbon dioxide. NASA's SphereX telescope mapped a vast CO2 coma stretching hundreds of thousands of kilometers, with much less carbon monoxide than expected. At the same time, common comet markers like CN were weak or absent in early spectra. In sum, Atlas is hyperactive. Roughly 1/5 of its surface seems to be venting gas, about 4 times the active fraction of typical solar system comets, and it contains odd chemical signatures. For example, astronomers even detected abundant neutral nickel, but virtually no iron in its coma. These surprises are forcing a rethink of comet models. Atlas's extreme CO, 2 to H2O ratio, and early water outgassing suggest it formed in a very cold, carbon-rich environment and has undergone a different thermal history than most comets we know. It may have been well baked and boiled in its home system before being flung here, meaning it lost more volatile ices like CO over time. Such findings challenge simple models of volatile retention and delivery. In fact, researchers now emphasize that no single formation recipe can explain all interstellar visitors. As one recent analysis notes, 3I Atlas appears chemically bizarre compared to solar system norms, underscoring a diversity of comet types in the galaxy. Planetary systems evidently eject a wide range of icy bodies, from dry, rocky fragments to carbon dioxide-laden giants, so our models of small body formation and evolution must accommodate that full variety. The scientific community is buzzing with these implications. Experts point out that each interstellar comet has upended prior expectations. First a barren asteroid, then a run-of-the-mill comet, and now a hyperactive, CO2-drenched interloper. Many observers stress that Atlas is a wake-up call. The chemistry it reveals is telling us that distant stars can make comets quite unlike anything in our solar system. In practical terms, astronomers are expanding their search strategies for the next visitor. With the Vera C. Rubin Observatory and other surveys coming online, we may find dozens of new interstellar objects each year. Atlas teaches us to watch for odd signatures, early water release at large distances, unusual gas ratios, or even exotic metal vapors, since no one model will fit all interstellar comets. By learning from this remarkable visitor, scientists will be better equipped to catch the full range of surprises that the next interstellar traveler may bring. In the grand sweep of cosmic time, interstellar visitors are extraordinarily rare. To date, astronomers have confirmed only 3 such objects passing through our solar system. The first, ʻOumuamua, 2017, was a strange, dry, cigar-shaped interloper with no detectable water or ice. The second, Borisov, 2019, turned out to be a true comet, active and glowing, but with an unusually high concentration of carbon monoxide in its tail. Now in 2025, we have observed 3I Atlas as the third interstellar visitor. Each has been unique, a lone messenger carrying material from another star system. The differences between them are striking. ʻOumuamua appeared to be a dense, rocky body with no hint of cometary gases, puzzling astronomers. Borisov, by contrast, developed a classic cometary coma and tail, but with more carbon monoxide than any solar system comet seen at the same distance. 3I Atlas has outdone both of its predecessors in activity. Observations show roughly 20% of Atlas's surface was actively venting gas, 4 times the typical active fraction of solar system comets. Its cometary atmosphere is overwhelmingly rich in carbon dioxide, with a CO2 to water ratio far higher than ever seen in another comet. In short, each interstellar visitor has told a different chemical story. These discoveries have upended any one-size-fits-all picture of comets. Every interstellar object carries the chemical fingerprints of its home system. Hubble images and spectroscopy of Atlas reveal ices and organics shaped by a distant environment. Detecting abundant CO2, along with water ice in Atlas's nucleus, was heralded as a major step forward in comparing comets from other stars to those in our solar neighborhood. In other words, Atlas's unusual makeup shows that planet-forming disks around other stars can produce a wide variety of comet chemistries. Astronomers call these travelers chemical ambassadors. Each one is a treasure trove of clues about the composition and evolution of faraway worlds. The brief visit of Atlas galvanized the astronomical community. As soon as it was identified, every telescope was trained on it. Space-based observatories and ground telescopes alike. We knew we had only one shot at this fleeting visitor. Hubble scientists noted that this fleeting encounter underscores the importance of observing such objects quickly before they disappear back into the cosmic dark. In practice, that meant coordinating observations across NASA's fleet, Hubble, JWST, Swift and others, and even orbiters around Mars to capture every bit of data before Atlas slipped away. And soon, it will be gone. Like its predecessors, 3I Atlas is on a one-way trajectory out of our solar system. After perihelion, it will fade back into interstellar space and never return. For a few short months, it was a messenger from another stellar system, granting us just a snapshot of its composition. We have learned what we can and stored the data. The rest of Atlas, ice, dust and rock, will vanish from view, leaving only the measurements we managed to collect. In the end, these rare interstellar encounters remind us why we look to the heavens. Each new cosmic stranger challenges our assumptions and sharpens our science. As one astronomer put it, having an object like 3I Atlas is like we get a sample of a planet orbiting another star showing up in our own backyard. The fact that we can track and study a piece of another solar system is a testament to human curiosity and technological progress. These fleeting visits expand our horizons and fuel our drive to explore. In that sense, the brief appearance of 3I Atlas is not just a moment of discovery, but a spark lighting the next chapter of cosmic exploration.